Hey everyone, welcome to our second recorded session for the semester. Today we begin looking at the chemistry of life, and we will be getting into a reasonable amount of chemistry. And one of the questions that I'm always asked right at the beginning of the semester when everyone starts to realize just how much chemistry there is in what is arguably a biology class is, why do we have to do so much chemistry? And the answer is somewhat simple to state, but it leads to a lot of complexity for the first 5 or 6 weeks of the semester, I guess. And the reason is something that I mentioned in the first session for chapter 1. And it's simply that a cell in its most simplest form can be considered to be a bag of water held by the cell membrane, in which a lot of chemical reactions occur. And so for all intents and purposes, a cell is just a bunch of coordinated chemical reactions. And so right there, we start thinking in terms of chemistry. And so if you really want to understand how a cell works, and by extension, how an organism, whether it be unicellular or multicellular, works, you really have to come to terms with chemistry. You have to have a fundamental understanding of chemistry in order to make sense of cellular functions. And one way that we like to refer to this is to think of chemistry and biology, and particularly that section of chemistry called biological chemistry or biochemistry. Those two disciplines, biochemistry and biology, are simply two sides of the same coin, and you can't separate one from the other. If you really want to come to terms with biology, you really have to come to terms with chemistry. Hence, we have the first 10 chapters of the semester focusing almost exclusively on chemistry. Chapter 6 is a little bit of an exception because it's looking at the fundamental structure of a cell, but even there we talk a little bit about chemistry. And chapter 1 is just an introductory chapter, so it really doesn't connect to chemistry, although I did mention a little bit about chemistry there. But this chapter represents the very beginning of our investigation of the chemistry of life. There are some breaks throughout the recording, as I mentioned yesterday, and as I mentioned in some of my postings. These recordings can be quite long and contain a lot of explanations about some reasonably complex ideas and concepts, and sometimes they take a little bit of time to wrap your mind around them. Some of it, and particularly today, is going to involve a lot of visualization. I do have some models that I'll show you, and in some of the upcoming chapters we'll be relying on models again as well to look at the structure of molecules. But a lot of it is going to come down to how much time are you going to spend thinking through these concepts, drawing diagrams based on what I've told you, based on some of the diagrams that I will sketch out this morning. It's going to take some time. And so if you find yourself being challenged, if you find yourself getting into a little bit of information overload as you're looking at these recorded sessions, by all means, stop at the breaks and walk away, but make sure that you come back again. And the breaks are going to be fairly regular, and they're going to be at the end of some of the sections that are pretty difficult to make sense of. I'll be the first one to admit that there are some challenges here. The first break comes fairly early on. It's not a particularly difficult section, but after that, we start getting into the more challenging material. But hopefully along the way, with the models, with drawings, with my explanations, I can help you come to terms with this. And of course, if you run into any trouble, by all means, come and talk to me in office hours, and we'll see what we can do to try and clarify some of the things that you're struggling with. So that being said, let me move through to the first slide. And basically, this is just stating something that should be really obvious to you, particularly if you've had any sort of background, if you've had even a modest amount of chemistry or a modest amount of biology, even if it's just middle school. Some of this is information that you are probably already aware of. So this should be somewhat of a review section. One of the things that we know from our experience is that the universe that we can touch, taste, feel, and manipulate, that part of the universe that is subject to our scientific investigation, is made up of something called matter. Matter has two very intrinsic properties that it has simply because it's matter. And that is that it occupies space or volume, and it has mass. Now, here on Earth, we think of mass and weight as being equivalent. But weight is not really equivalent to mass. And you can illustrate that fairly simply. Here on Earth, if you weigh 200 pounds, that is also considered to be your mass. The mass and your weight are equivalent. But if I was to transfer you somehow to the moon, your mass on the moon would still be 200 pounds, but your weight would only be around 65 pounds. And that's because gravity on the moon is only 1/16 of gravity here on Earth, and weight is a function of gravity pulling on mass. You can further illustrate that by thinking about the astronauts that are on the International Space Station. We refer to them as being weightless. They have no weight because the movement of the space station counteracts the pull of gravity, and so they don't feel anything. They are weightless, but they still have mass. Their body size hasn't changed. The amount of material in their bodies hasn't changed, so they still have mass. So this is what we refer to as intrinsic properties. And of course, matter comes in three states: solid, liquid, gas. We're familiar with those. Once we start looking at what the smaller subunits of matter are that constitute the universe as we can see it and manipulate it, we recognize that there are 92 different types of units that make it up. We refer to those units as elements, and each element is constituted by an atom. An atom is the smallest unit of an element that has all the fundamental chemical properties of that element. So if you were to take a piece of aluminum, for instance, and slice it and dice it until you got down to a single atom of aluminum, that would have all the chemical properties that we associate with aluminum. It would be the smallest unit that has all of the properties that we associate with aluminum. Now, we will be talking about the properties of some of these elements because they constitute the elements that are found in living organisms. But of the 92 naturally occurring elements, only 25 turn up in living organisms. So immediately we reduce the number of atoms that we have to worry about, or the number of elements that we have to worry about, quite substantially. But as you'll see shortly, we can even reduce the number to a much, much smaller number and still account for the vast majority of atoms found in living organisms. What we also know is that with the exception of a small handful of atoms, atoms do not exist in isolation as individual atoms. They group together to form complexes of atoms, which we can refer to as molecules, or we can refer to as substances or compounds, depending on the nature of the association between the atoms. If the atoms are bound together through sharing electrons, the strongest form of chemical connection between atoms, then we refer to them as molecules. If, however, they are linked together by some other arrangement, by simple electrical attraction or something like that, then we no longer refer to them as molecules. Molecules are atoms strongly bonded together by sharing electrons, and we'll talk more about that in the third section of the presentation. Then if they're not held together by these shared pairs of electrons, then we refer to them as compounds. And compounds are simply substances made up of multiple types of atoms or multiple elements, where the ratios or percentages, relative percentages of those elements are constant. And something that you might be familiar with that falls into this is table salt, sodium chloride, where the ratio of sodium and chlorine atoms is 1:1. And that is consistent no matter where you find table salt or sodium chloride. And it doesn't matter how big a mass of sodium chloride you have or how small a mass of sodium chloride you have, the ratio of sodium to chlorine is always 1:1. So it would constitute a compound, but it is not a molecule. There's no such thing as a sodium chloride molecule, and you'll understand more when we talk about chemical bonding. So I have a couple of slides in this presentation that are actually slogans that you can get from t-shirts. My daughter, when she was much younger, used to prowl t-shirt sites on the internet, and when she found some interesting ones, she'd let me know about them. And this is one that she discovered. Never trust an atom, they make up everything. Yeah, it's a bit of a cheesy joke, but hey, there's no reason why we can't have a little bit of fun along the way here. This is a pretty heavy duty topic, so let's try and have a little bit of fun as well as we go through it. So as I mentioned, there are only 25 elements that make up or commonly make up living organisms. But of those 25, about 96% of all the atoms in your body are represented by 4 elements: carbon, hydrogen, oxygen, and nitrogen. So as we talk about the chemical concepts that we need to talk about this today in this presentation, we're going to spend most of our time focusing on carbon, hydrogen, oxygen, and nitrogen. And that's going to simplify a lot of the concepts, because these are relatively simple atoms in terms of their makeup. And that means we don't have to delve very deeply into some of the more complicated concepts that we need to deal with today. So 96% of all the atoms in your body are carbon, hydrogen, oxygen, and nitrogen. And you may ask, why? Well, one of the reasons why is because 70% of the material in your body, let me fire up the pen. So 70% is water, H2O. So that accounts for why hydrogen and oxygen are there, and they're usually listed as number 1 and number 2 on the list. Sometimes oxygen is number 1, sometimes hydrogen is number 1. Typically, it would be hydrogen that is number 1. So, but that just the fact that your body is 70% water accounts for the presence of hydrogen and oxygen. Okay, the remaining 30% is molecules built on carbon skeletons. And we'll talk a lot more about that in chapter 4. So this accounts for the presence of carbon. And then nitrogen is listed as number 4. And the reason for that is that these carbon skeletons include, let me get the eraser up because I didn't want to put that there. Take that out. Hydrogen, oxygen, and nitrogen attached to the skeletons. Combinations. And we'll look at that in a lot more detail when we get to chapter 5. So in upcoming chapter, well, chapter 3 is going to talk about water. It's all about the properties of water. Chapter 4 he's going to talk all about carbon and why carbon, and talk a lot about the carbon skeletons. And then in chapter 5, we're going to talk about the different types of molecules that are built from these carbon skeletons, including these combinations of hydrogen, oxygen, and nitrogen that are attached to the skeleton. So there's a lot more coming up in the next 3 chapters that are going to expand on this basic idea that these are the 4 basic elements that make up so much of life. So here's the table that presents, and this is taken straight out of your textbook, that presents the 25 elements that are found in living organisms. Here are the 4 big ones that account for 96% of all the atoms in your body. Then you'll notice these ones are present and make up pretty much the remaining 4% thereabouts. So what about all these others down the bottom here? These are called trace elements. These we don't need very much of. Tiny, tiny amounts. In some cases, only several hundred atoms of some of these elements, but they're critical. If you take a vitamin and mineral supplement, the mineral supplement of these trace elements, we need tiny, tiny amounts of them, but nonetheless, we need small amounts of them. And typically we get these from eating plant material. So if you actually eat a diet that is rich in fruits and vegetables, you're probably getting all the trace elements that you need. You don't need to supplement those. Likewise with the vitamins, if you're eating a diet that's rich in fruits and vegetables, you'll get all the vitamins that you need. You really don't need a supplement. And in some cases, we now recognize that taking supplements can actually be bad for us because there is such a thing as too much of a good thing. And so if you're getting a sufficient amount of nutrients, supplementing them may not be a good thing. And some supplements actually contain more of the vitamins that you actually need. And it's not a good thing to get too much of some of the vitamins, very particularly. We might talk a little bit more about those in a later chapter if we have some time. So why these? Well, calcium in bones, phosphorus in bones, potassium is useful in cells, but particularly for nerve cells. Sulfur is found in protein. Sodium used in nerve cells in conjunction with potassium, but we don't need a lot of sodium. But we get way too much sodium because of sodium chloride. We typically get way too much table salt. Chlorine is also useful in cells as a negative ion inside cells. Magnesium is also a useful element for supporting chemical reactions, or more precisely, the enzymes that regulate chemical reactions. And again, we'll talk more about those in chapter 8, and we'll talk about the role of some of these trace elements when we get to chapter 8, because a lot of these are involved in helping regulate enzymes, or allowing the enzymes to work at their most efficient rates. So these are all the elements that are found in living organisms, but remember, these 4 account for the vast majority of it, about 96%. And so as we talk about the chemical principles that we need to focus on in this chapter, these are the elements that we're going to focus on mostly. So first concept check. We talked about last week, or in the last, not last week, in the last presentation, this idea of emergent properties, the fact that you can't always understand the properties at one level of the hierarchy by looking at the properties present in the next lowest level of the hierarchy. So table salt has a certain set of properties. You're probably familiar with some of them. Why does table salt have emergent properties, or what sort of emergent properties does it have? So I'll stop for about 30 to 45 seconds, give you a chance to think over this one, and then we'll discuss it. Okay, so let's think about this for a minute. If we take a look at the individual properties of sodium and chlorine, sodium is a metal. As you'll see when we look at a periodic table a little bit later, it sits over on the left-hand side of the periodic table, on the far left-hand side, in fact, and that's where all the metals hang out on the periodic table of elements. So sodium is considered to be a metal, but it's a very soft metal. It's shiny gray when you cut it freshly, but if it sits around in the air, it starts to tarnish very, very quickly because it's very reactive with oxygen and water in the atmosphere. In fact, if you drop a little bit of sodium, pure sodium, into water, it hisses and bubbles, there's lots of flames, and then you'll get a little bit of an explosion because it's also releasing hydrogen gas as it's reacting with the water, and that will catch on fire very explosively. You do not handle sodium with your bare skin because the sodium will react with the moisture in your skin. You have to keep sodium under liquid paraffin oil so that it doesn't react with the moisture in the air. And you can cut it with your fingernail. It's maybe a metal, but it's very, very soft. You can cut it with your fingernail and you can easily cut it with a knife. So that's sodium. Chlorine, on the other hand, sits way over on the right-hand side of the periodic table. It is also very reactive, but it's a gas and it's poisonous. In fact, it was one of the first biological warfare or chemical warfare substances ever used. The Germans figured out how to capture it in large quantities and put it into tanks, and they would carry these tanks up to the front lines in World War I. And when the wind was blowing in the right direction, release the gas into the air so that it would blow over the front lines of the Allied soldiers. The Allies, in return, figured out how to do it, and this became the first form of chemical warfare. And chlorine is a very, very nasty gas. It is yellow-green in color. And if you were to breathe it in, it would react with the water in your lungs and form hydrochloric acid, which would eat your lungs, or it could make you blind. And if you get enough exposure, it will actually kill you. It is considered to be very, very toxic. Yet when you combine sodium and chlorine together to get sodium chloride, you get something that has properties that are not evident by looking at the properties of sodium and chlorine individually. And so all of the properties of sodium chloride as a substance are emergent properties. It forms a white crystalline material that is very soluble in water and doesn't react when you dissolve it in water. It is not lethal to organisms unless you were to eat huge quantities of it, which no one would in their right mind do. The sodium itself and the chlorine itself, as the breakdown products of sodium chloride, are very useful inside cells. They're not typically considered to be toxic. So there's a lot of things about sodium chloride as a substance that's not obvious by looking at the chemical properties of sodium and chlorine. So the elements sodium and chlorine have their own unique properties, but the properties of sodium chloride, the substance, which is at the next level of the hierarchy above sodium and chlorine as elements, are not obvious from the properties of sodium and chlorine as elements. So that's why table salt has emergent properties. So let's move on to the next section. So we need to talk a little bit about the structure of atoms. Hopefully this is a refresher. I mean, most people have a familiarity with the structure of atoms. And as I mentioned earlier, the atom is considered to be the smallest unit of an element, and it has the chemical properties of the element. And structurally, we recognize that atoms are made up of three particles, and you should be familiar with these particles. The protons, which are found in the nucleus, they have a positive charge, and The number of protons in the nucleus is referred to as the atomic number, and that defines what element the atom belongs to. So let me just make sure the pen is working still. Yeah. So all carbon atoms have 6 protons. So if you have an atom that has 6 protons, irrespective of what else it has, it's a carbon atom. Likewise, oxygen atoms have 8 protons. This is why the number of protons is called the atomic number, because it really does define what element the atom belongs to. Each element is assigned a number on the basis of the number of protons that are present in the atom. So all carbon atoms, for instance, have 6 protons. All oxygen atoms have 8. All chlorine atoms have 17 protons. The other particle that's found in the nucleus is called the neutron. It has no charge, hence the name neutron. It is neutral. And protons and neutrons, for our purposes, are considered to have exactly the same mass, and that mass is given as 1 Dalton. So a Dalton is simply a unit of mass that was developed to allow us to measure the mass of protons, neutrons, and to some degree electrons, but more specifically to measure the mass of atoms and molecules, because the normal units of mass that we would use simply don't work. They're too big, and atoms are too small in order to be measured conveniently using those units. So the Dalton was developed as a unit of mass appropriate for measuring the mass of atoms and molecules. So when we start thinking in terms of the mass of an atom, as the slide says here, it's the protons and the neutrons, the combined number of protons and neutrons that give us the atomic mass. So the number of neutrons can be different in atoms of the same element, as you'll see. So the number of neutrons is not necessarily fixed for all the atoms of a particular element. But given that the atomic mass equals the number of protons plus the number of neutrons, if we take the atomic number sorry, let me erase this, because that's not going to be right. If we take the atomic mass and subtract the atomic number, then that will equal the number of neutrons. So if you're ever asked to figure out the number of neutrons in an atom, which you may very well be asked to do, if you take the atomic mass, which you can get from the periodic table, and you subtract the atomic number, which is the number of protons, then you'll be able to calculate the number of neutrons. And as you'll see, the number of neutrons is variable. More on that in a minute. So we haven't talked about the third particle, and you notice we haven't even mentioned it here in terms of determining the mass of an atom. So everyone is probably aware that the third particle is the electron. It has a negative charge. It circulates in the space around the nucleus where the protons and the neutrons are found. It's a bit more complicated than that. And in fact, one of the most challenging parts of this chapter is trying to visualize where the electrons actually are. More of that as we move through. But what we do know is that in an electrically neutral atom, the number of protons and the number of electrons are equal. Electrically neutral. And that's an important observation, as you'll see. So why do we not consider the mass of electrons when we calculate the mass of an atom? For a simple reason. Electrons, and I'm going to show you an abbreviation, which is E minus, because I like to use these abbreviations. It's a little bit easier than writing out electrons all the time. Have a, yeah, let's try and write a little neater, I think. So an electron has a mass of 1/2000 daltons. Why is that significant? Well, uranium, which is the most massive of the naturally occurring elements, is element number 92. That means it has 92 protons and therefore 92 electrons. And so the mass of electrons in the heaviest naturally occurring element on Earth, uranium, is still only 92/2000 daltons, essentially nothing when you think about the total mass of an atom. And so we simply do not calculate the mass of the electrons into the atomic mass when we do so, because their total mass is negligible. So as far as we are concerned, as biologists or biological chemists, as we are most correctly describing ourselves as right now, we don't have to worry about the mass of the electrons when we do the mass of an atom. We just worry about protons and neutrons. So these are the three particles. We're going to spend a lot of time talking about electrons, however. We will talk a little bit more about protons and neutrons, but most of our discussion today is going to be about electrons, because in the end, the reactivity, so the chemical reactivity, and the available energy So when we want to talk about chemical reactivity, when we want to talk about energy, and particularly energy manipulation in chemical reactions, it's all about the electrons. And so a lot of what we'll be talking about today and the principles that we're carrying forwards from from this chapter into the upcoming chapters where we start talking about chemical reactions, all of that is going to hinge on understanding the electrons and the nature of the electrons and how they can be manipulated. So that's why we spend a lot of time talking about electrons. You'll see more as we move through this. So these are the two ways that we can think about electrons. Typically, we represent them as solid particles, usually associated with a circle drawn around the nucleus. So this would be a legitimate diagram of an atom. But it is more precise to think about electrons as a cloud of negative charge, rather than to think of them as actual physical particles, because it turns out that electrons can be both particles and clouds of charge or waves at the same time. And they actually do physically exist as the two ideas at the same time. This gets really difficult to understand at times. It's really tough to imagine that this is the situation. But we do have to think that way because it becomes important to our understanding of energy manipulation in later chapters. And so we do have these two fundamental ideas about electrons. They can exist as particles, but they can equally exist as charges of negative charge. And how you interact with the electrons determines what you're going to see. Are you going to see the negative charge field, or are you going to actually see particles? You can't see both at the same time, unfortunately. You can see one or you can see the other, but you can't see both of them at the same time, even though both exist at the same time. But as soon as you start trying to think about electrons as particles, you no longer see them as charge clouds. As soon as you start thinking about and interacting with electrons as charge clouds, you no longer see them as particles. Yeah, I know it's a little bit confusing, but that's what we understand. We have to be able to be mentally flexible enough to accept that idea and run with it, because it becomes important to our further understanding of chemical reactions and energy manipulation in chemical reactions. So you hopefully you recall from a couple of slides back that I mentioned that the number of neutrons in an atom is flexible. The way we know that this is the case is by looking at the mass of atoms from a particular element. And we can do this with highly specialized machines called mass spectrometers. They actually allow us to measure the mass of individual atoms. And when we do that, we find that the atoms of a particular element don't all have the same mass. Now, remember, what defines what element an atom belongs to is the number of protons in the nucleus. So that can't change, because if you change the number of protons, you're actually changing the element the atom belongs to. So you can't change that. So if there's an increase in mass, and the mass is the sum of the number of protons and the number of neutrons, and the number of protons simply cannot be changed, or you're changing the element, then it stands to reason that what is changing is the number of neutrons. And so if we think in terms of carbon, number 6, element number 6, has 3 different atoms, or to use the correct term, isotopes. Carbon 12 has 6 protons and 6 neutrons. Carbon 13 has 6 protons. It is carbon, so it's going to have 6 protons. Where does the extra mass come from? It's got 7 neutrons. And then carbon 14, let me see if I can move this out of the way somewhere. over here for a moment. It also has 6 protons. It is carbon after all, but it has 8 neutrons. And this one, carbon-14, happens to be radioactive, which is true for a number of isotopes. They are radioactive. Now, you may also recall that I said that chemical reactivity is a product of the electrons. So if we remember that the number of protons and the number of electrons are the same in atoms, because these 3 isotopes of carbon all have 6 protons, they must also have 6 electrons, which means that chemically they're going to be exactly the same. They're going to react exactly the same. Even though carbon-14 happens to be radioactive, chemically it's going to behave exactly like carbon-12, which means that carbon-14 can be used to follow chemical reactions, because you can see where the carbon-14 is. It is radioactive, it gives off energy, but chemically it's going to behave in chemical reactions exactly the same way as carbon-12. So when we talk about cellular respiration in Chapter 9 and photosynthesis in Chapter 10, both of those chemical pathways were figured out by following carbon-14 through the chemical reactions. Because you could track where the carbon-14 was, it's radioactive, but chemically it was behaving just like its non-radioactive cousin, carbon-12. And so those of you who are heading for the medical field, which I suspect is most of you, a lot of students in this class are going into the medical fields. So if that's you, you're going to learn a lot more about the use of radioactive isotopes in medicine somewhere in your medical education, because the use of radioisotopes for diagnostic purposes and also for treatment purposes is very, very widespread these days. There are so many uses that we can make of radioactive isotopes. And now you know where those isotopes come from. They are simply different forms of atoms from the same element. Why are they different forms? Because they have different mass, and they have that different mass because they have different numbers of neutrons. Remember, the number of protons can't change, because if you change the number of protons, you change the element. It's the number of protons that determine what element an atom belongs to. So you can't change the number of protons, but you can change the number of neutrons and therefore change the mass. And in some cases, adding extra neutrons or subtracting neutrons, because the number of neutrons could be less in some isotopes, changes the isotopes so that some of them will be radioactive. Not all isotopes are radioactive. There are some elements, lead is a good one, where all the isotopes are actually non-radioactive. Lead is extremely stable. But in a lot of other elements, adding some extra neutrons or taking a neutron away means that the isotope is now unstable. It's radioactive in some form. And so we can use those in all sorts of ways as diagnostic tools to track chemical reactions, to diagnose diseases, and in some cases even to treat diseases. Cancer can be treated using a radioactive isotope of the metal cobalt called cobalt-60. It's intensely radioactive. And that intense radiation energy can be used very carefully to bombard tumors that are buried deep in tissues where a surgeon could not go in and cut out the tumor. But the radiation can kill the cancer cells. So there are all sorts of uses of radioactive isotopes in modern medicine. And if you're headed into medicine, you're going to learn at some point a little bit more about the use of radioactive isotopes. So now we have to focus very much on the electrons. And this is where it starts to get a little bit more complicated because of the nature of the spaces that electrons occupy. So when we draw a diagram of an atom and we draw the location of the electrons as a circular orbit around the nucleus, we're actually misrepresenting what the situation actually is, because an atom is not two-dimensional. When we draw a diagram of an atom on a sheet of paper, we're drawing it in 2 dimensions, but we have to remember that an atom is 3-dimensional. And so while a circle is a nice representation of the spaces occupied by an atom, we really need to, an electron, we really need to remember that these spaces are 3-dimensional. And that means the 3-dimensional equivalent of a circle, which is a sphere. So really, electrons are occupying spherical spaces around an atom. And those spherical spaces are referred to as energy shells or electron shells or energy levels. And the reason why is because there is energy associated with the position of those electrons in those energy shells. So I'm holding a pen in my hands, and you can see this in the video. And I'm holding that pen above the desk that I've got my computer sitting on. And as a consequence of the pen's location above the desk, sitting in a gravity field with gravity wanting to pull the pen downwards, the pen has energy. That energy is called potential energy, and it has a certain amount of energy because of its physical location with regards to the desk. If I move the pen down, because it has a shorter distance to fall, I now know that it has less potential energy. If I raise it up further, because it can now fall a lot further distance, it has more potential energy. So the amount of potential energy the pen has is a direct reflection of the distance it is away from the desk. The closer it is, the less energy it has because it can fall a shorter distance. The further it is away from the desk, the more energy it has because of the distance that it can fall. It can fall a greater distance. Now, it's a little bit more complicated than that. And when we get into chapter 8 and we talk about energy manipulation and energy concepts and the rules that govern energy manipulation, we'll talk a little bit more about potential energy and physical locations. But what we need to bear in mind is that if we look at an atom again, and we think in terms of where the electrons are, if this is the nucleus in the center, let me change the color here, then the 3-dimensional spaces that are occupied by the electrons, and again, I've got to do it in a 2 dimensions, are at fixed distances away from the nucleus. And because there is a positive charge on the nucleus, it's got all the protons in it, and the electrons sitting out here have a negative charge, there is a natural pulling force between the nucleus and the electrons, just as there is a pulling force on my pen when I hold it above the desk. And so the electrons have potential energy as well. And the amount of potential energy that they possess is a reflection of which energy shell or electron shell they happen to be in. So an electron sitting in this energy shell has less energy, potential energy, than an electron sitting out here in the energy shell further away from the nucleus. So electrons do represent a source of energy. Now, it's a little bit more complicated than that as well, because it turns out that electrons are able to move from one energy shell to another energy shell, and the direction in which they move is a reflection of the amount of the energy change that's occurring. So if you want to move an electron from an inner energy shell to an energy shell that's further out, you have to put energy in, and that the energy that you have to supply has to be equal to the energy difference between the two energy shells that the electron is moving between. So an electron can move from a lower energy shell to a higher energy shell, but there has to be an input of energy, and that input of energy has to be equivalent to the energy difference between the two energy shells that the electron is moving between. Now, when it moves out, it enters what is referred to as its excited state. That's not very neat. Neither is that. Bear with me for a minute. I'll get it right. So when they move out to these higher energy shells, they're in an excited state. They're in a higher energy state. They don't want to be there. They want to come back again to what is referred to as their resting state, their point of origin. So when they come back to their resting state, or ground state, which is another term that's used, they have to shed the energy that they gain to move out to their excited state. So energy is lost. And sometimes that energy that's given off is visible. You can actually see it. And when you can see it, we call it fluorescence. And we'll come back and revisit fluorescence again in later chapters, because they become really important. It becomes an important concept in later chapters, as does this whole notion of energizing electrons, particularly when we start talking about photosynthesis, because it's in energizing electrons that plants capture light energy. And we'll talk a lot more about that when we get to chapter 10. And extracting energy out of electrons in chemical reactions is part of what we need to discuss when we talk about cellular respiration. And we'll talk about this staircase concept. And I will actually use that terminology, a staircase idea, when we talk about this. So these are all ideas that are going to have real consequences or real connections in later chapters. So it's really important that you come to terms with this right now. So if you find that you're struggling with this, spend the time, take the time to make sure that you square this away, that you understand this ability of electrons to move from lower energy shells to higher energy shells, and what that means. It means that you are adding energy to them when they come back. When they move out, when they come back to their resting state, energy is being released. This is the heart of understanding energy manipulation as far as life is concerned. Capturing light energy by energizing electrons, extracting energy out of molecules by moving electrons to lower energy levels. This is really what energy manipulation is all about in life. This is how we understand how living organisms manipulate energy. It's all about manipulating electrons and the energy of electrons. So this is a fundamental idea. I can't stress this enough. So it's really important that you come to terms with this one. So when we start thinking in terms of the actual energy shells that are occupied in a particular atom, there is one energy shell that becomes critical, because it's not just any electrons that determine chemical reactivity. It's electrons in a particular energy shell that determines chemical reactivity. And that chemical shell is, or that energy shell is referred to as the valence shell. Now, the valence shell differs from element to element depending on where it's located in the periodic table. And we'll look at a periodic table in a moment. But the valence shell could be any of the energy shells or any of the electron shells that have electrons in them. Specifically, however, the valence shell is the outermost shell that contains electrons. So if it's the innermost energy shell, what is referred to as shell number 1, or the first energy shell, that is the one that has electrons in it, that would be the valence shell. If it's shell number 2, that would be the valence shell. If it's shell number 3, that would be the valence shell. Any of the shells could be the valence shell, but the particular one is, which is the outermost shell of an atom that contains electrons. That is the one that is referred to as the valence shell. So let's take a look at a periodic table and see what that means. So here is a simple periodic table. It only contains 18 elements. The full periodic table contains not only the 92 naturally occurring elements, but it actually contains listings of elements out to number 118 are currently recognized, although there's evidence for elements out to 121, I believe. The elements that are above 92, in other words, above uranium, are artificially created elements. We have made those here using atomic reactors and manipulating elements to create those heavier elements, and they are extremely unstable. The only reason why uranium is present on the planet is because it is stable enough. It is radioactive, and all isotopes of uranium are radioactive, but they are stable enough that there's still some uranium left on the planet. But for elements above 92, their stability is so low that if there had ever been any of those elements on Earth early on, they've all disappeared, they've all broken down since the Earth formed. So we have elements 1 through 92 as the naturally occurring elements. So what do we find in the periodic table? Well, the first thing we need to recognize is that it gives us some information. Number 1, it tells us the name of the element. Number 2, it tells us the atomic number of the element. It tells us the symbol of the element. And then it may also provide information about the atomic mass, depending on how the numbers are arranged. So this simple one is only giving us the name, the symbol, and the atomic number. It's not telling us anything about the mass. But in a more complete periodic table, you'll also get the atomic mass, and you might get some other information as well. But the fundamental information that most periodic tables are going to give you is the name, the symbol, the atomic number, and the atomic mass. And from that, you can then start to draw out diagrams of the atoms, because then you know the number of protons plus neutrons, that's the mass. You know the number of protons, that's the atomic number. You know the number of electrons, because that's equal to the atomic number. You know the symbol to use for it. You know the name to use for it. So you've got a lot of information about that allows you to draw diagrams of atoms. So let's take a look and see what we've got in this periodic table. What can we learn about the number of electrons? Because really that's what's important thing here, and also the valence shell. So elements number 1 and 2, hydrogen and helium, occupy the first row of the periodic table because the electrons that are found in energy shells for atoms of hydrogen and helium occupy the first energy shell. So the first row of the periodic table is talking about the first energy shell around the nucleus. So hydrogen is element number 1. It has 1 proton. Consequently, it also has 1 electron, and that electron occupies the first energy shell. Element number 2 is helium. It has 2 protons. It also has 2 neutrons, so it has a mass of 4, and the 2 electrons occupy energy shell number 1. And because this is the smallest energy shell, that's the total number of electrons that you can fit in here. And there are reasons for that we'll get into a little bit later. So when we come to element number 3, lithium. Lithium is now in the second row of the periodic table, and we're starting to put electrons into energy shell number 2. So lithium has 3 protons, therefore 3 electrons. 2 of the electrons are in energy shell number 1. The third electron is in energy shell number 2. And so energy shell number 2 now becomes the valence shell for lithium. And in fact, for all the elements in the second row of the periodic table, the second energy shell is the valence shell. For the elements in row number 1, the first energy shell is the valence shell. So in some sense, you can look at the row of the periodic table and determine which is the valence shell. So row number 1 means the valence shell is energy shell number 1. Row number 2 means the valence shell is shell number 2. Row number 3, the third energy shell is the valence shell. So as we move across, each subsequent column, column 1, 2, 3, 4, 5, 6, 7, and 8, tells you how many electrons are in the valence shell. So the row tells you which shell is the valence shell. The column tells you how many electrons are in the valence shell. So in row 1, column 1, 1 electron in the first energy shell, which is the valence shell. Now you'll notice that helium is not sitting over column number 2, it's right over here in what is arguably column number 8. Again, there's reasons for that. We'll talk about that in a moment. When we get to energy shell number 2, which actually plays out the principle that I'm trying to illustrate here, row number 2, second energy shell, that's the valence shell. First column, 1 electron in the valence shell. Column 2, which is beryllium, 2 electrons. Column 3, boron, 3 electrons. Column 4, carbon, 4 electrons. Nitrogen is in column 5, 5 electrons. Oxygen is in column 6, 6 electrons. Fluorine is in column 7, 7 electrons. Neon is in column 8, and 8 electrons. Now remember, we're talking about the electrons in the valence shell. There are always going to be 2 electrons in the innermost shell for elements in shell number 2. So we've got to remember that there's more than just the electrons in the valence shell. There's also the electrons in the innermost shell. But chemical reactivity is all about the electrons in the valence shell, so that's where we're focusing. So as we move across, we're talking about increasing number of electrons in the valence shell. The row tells us which shell is the valence shell. So just to reinforce the principle, shell number 3 or row number 3 is the third energy shell. That's the valence shell. Sodium is in column 1, so 1 electron in the valence shell. Magnesium is in the second column, so it has 2 electrons. Aluminum is in column number 3. It has 3 electrons. Silicon has 4, phosphorus 5, till we get to argon, and there's 8 electrons in the valence shell. So now we come to another principle that we have to recognize, and that is a principle called the octet rule. Oct means 8. So the octet rule is talking about having 8 electrons in the valence shell. There's something magical about that. with one exception, the first valence shell or the first energy shell, where you're restricted to only 2 electrons. You could never have 8 in there. And what the octet rule basically says is that when you have 8 electrons in your valence shell, with the exception of the first energy shell, where you can only fit 2, the elements that have that 8 electrons in the valence shell are chemically inert or unreactive. They don't combine with other elements. And we refer to them as the inert gases. So these are the inert gases. And the reason why is because they have a valence shell that contains 8 electrons, with again the exception of helium. But it still follows this. Helium is an inert gas. It doesn't interact. Atoms of helium do not chemically interact with other elements or atoms of other elements. They don't have to, because the valence shell is complete. So why is this important? Why is the octet rule important? Because it turns out that all the elements in the other columns are trying to arrange the number of electrons in their valence shell to look like one of the inert gases. And what they do in terms of rearranging the electrons in the valence shell depends on which of the inert gases happens to be the closest to them. So what do I mean by that? Well, let me show you again with the second energy shell. Lithium has 1 electron in its valence shell. If it got rid of that 1 electron, it would look like helium, because it would have the inner shell now as the outermost shell, and it's got 2 electrons in it, it's full. Or it could gain 7 electrons to look like neon, which also has 8 electrons in its valence shell and is therefore considered to be full, and actually is full. So the question then becomes, is it easier for lithium to gain 7 extra electrons or simply shed 1? And obviously the answer is to shed 1 to look like helium. And that's what it actually does. It will quite willingly give up its 1 electron. Beryllium either needs to shed 2 or gain 6. And again, as you might guess, it's easier to shed 2 than to gain 6. So it does. Boron could either gain 5 or shed 3. And again, it's easier to shed 3 than to gain 8, so it gets rid of its 3. Carbon, sitting in column number 4, is the tipping point. It could either gain 4 or shed 4. It turns out that it's a little bit easier to gain 4 than to give up 4. So carbon preferentially gains 4 to fill out its valence shell to look like neon. Nitrogen, no guess now, it's easier to gain 3 than to shed 5, so that's what it does. Oxygen to gain 2 than to shed 6. Fluorine to gain 1 than to shed 7. So as we move from left to right across the periodic table, the behavior of the elements to try and look like these noble gases changes. So long as it's the number of electrons to be shed is less than 4, they will willingly give up those 4, or at least they will give up those 4, some more easily than others. Once you get to 4 in the valence shell, then it's always a little bit easier to gain 4 than to shed 4. So now it becomes gaining, and it becomes increasingly easier to gain than to shed as you get further to the right. And the same is true for all of the shells. So if we were to come down here and look at the third energy shell, it would be the same thing. Now notice that I'm not talking much about the third energy shell. Why? Well, remember, hydrogen, oxygen, carbon, and nitrogen make up 96% of all the atoms in your body. Here's hydrogen, carbon, nitrogen, and oxygen. They're all either involving the first energy shell or the second energy shell. So we're not going to really go much further than the first and second energy shell in talking about these chemical principles, unless it is important to explain the principle in a little bit more detail by going to the third energy shell. But I don't want to go there unless I really have to. And so I'll stay away from the third energy shell. And the complexities that increase by talking about those shells only when it's really, really necessary to do so. So now we're starting to get some explanations about the chemical behavior of the atoms. Their chemical reactivity is a function of how many electrons are in the valence shell. What they do with those electrons in the valence shell depends on how easy it is for them to either give up an electron or gain electrons in order to look like the inert gases, which is the ultimate standard. Each element wants each atom wants to arrange its electrons so that it looks like an inert gas, that it doesn't have to interact with other elements, because it has a full or completed valence shell according to the octet rule, not according to the number of electrons that could fit into the valence shell, but according to the octet rule, which says 8 is the magic number. If you've got 8 electrons in the valence shell, then you're chemically inert, with the exception, of course, of helium, because it's only dealing with the first energy shell, and hydrogen under those circumstances as well. So we're starting to learn a little bit more about chemical reactivity. So now we have to start thinking in terms of not just energy shells, but something that is related to energy shells. And people tend to get these a little bit confused by virtue of the fact that there is this misunderstanding, I guess, that the term orbital and energy shell are interchangeable. And the truth is they're not. If you want to think of it in terms of something that might make sense to you, think of it in terms of Venn diagrams or some sort of diagram where you have an umbrella term, energy shell, but then you have a subset of that called orbital, because that's essentially what it is. An energy shell is a three-dimensional space that surrounds the nucleus. Orbitals are subsets of that three-dimensional space in a particular energy shell. Now, if we think in terms of the energy shells, and perhaps I should go back to one of the earlier diagrams, energy shells are like those Russian dolls where there's a doll inside a doll inside a doll inside a doll, a nested set of dolls. The energy shells are a nested set of three-dimensional spherical spaces. So you've got the inner shell occupying a small volume. The second energy shell being further out occupies a larger volume. The third energy shell being even further out occupies an even larger volume. And the orbitals are simply subset spaces created from or derived from the total three-dimensional space of an energy shell. Now that may seem a little bit confusing, so let me talk about it in another way that might make a little bit more sense to you. So let me move the text box out of the way a little bit. Let me move it all the way over so that I can draw over here. Turn on the pen, make sure it's working. So an idea that I got from listening to a chemist or a physicist talk about this many years ago struck me as a good way of trying to understand this, because I think it kind of makes sense. You could think of the nature of the energy shells and the orbitals in those energy shells as a apartment building, but it's a weird sort of apartment building. It's an inverted pyramid. So the bottom floor is the smallest floor, and it has a single apartment in it. The second floor is bigger, and because it's bigger, it can be subdivided into 4 apartments, all the same size as the apartment on the first floor. The third floor is bigger still, And because of that, it can be subdivided into 10 apartments. Again, all the same size as the previous apartments. If we go to the 4th floor, it's even bigger and it can be subdivided into more apartments still. In total, we know of this building, or this apartment building, has 7 floors. In other words, we know that there are 7 energy shells. So this is energy shell number 1. This is energy shell number 2. And this is energy shell number 3, and so on. Up we go. So this is the nature of the energy shells around the nucleus. So the first energy shell is the equivalent of the 1st floor of the apartment building, and it has room for a single apartment. The 2nd floor of the apartment building is the equivalent of the 2nd energy shell, and it has room for 4 apartments or 4 orbitals. Energy shell number 3, being bigger, has room for 10 apartments or 10 orbitals. So energy shell is equivalent to the floors of the building. Orbital is equivalent to the apartments. So when we take a look at the orbitals in an energy shell, there is always in each energy shell a spherical orbital. It actually is a sphere in much the same way as the energy shell itself is a sphere. And it's referred to as an S orbital. And in the first energy shell, it's the only orbital that's available. So it is called the 1s, the spherical orbital in the first energy shell. When we get to the second energy shell, there's also an s orbital, but because it's in the second energy shell, it's called the 2s. And then there are 3 extra orbitals called p orbitals, and they are given the designation 2p. But those are oriented on the 3-dimensional axes of 3-dimensional space, x, y, and z. So one is 2px, one is 2py, and one is 2pz. When we get up to the third energy shell, and I'll just do this to reinforce the principle, there is a 3s, and a spherical orbital, and it's in the third energy shell, so we call it the 3s. There are p orbitals, so there's a 3px, a 3py, and a 3pz. And the remainder are called d orbitals, so there are 5 3d orbitals in total. As we go. So this is how we start to understand the nature of orbitals in energy shells. Now, we're not going to worry anymore about the 3D space or the third energy shell, because we're not interested in atoms that have the third energy shell. Remember, we're thinking in terms of hydrogen, oxygen, carbon, and nitrogen, and they only involve the first and the second energy shell. They don't involve the third energy shell and so on. So the question then becomes, what is the importance of these orbitals and these energy shells, in these energy shells? Well, those are the locations of the electrons, and they also determine chemical bonding. So here you can see a diagram showing the spaces that are occupied. So this is actually neon. It's an inert gas. It's got 2 electrons in its first energy shell. It's got 8 electrons in its second energy shell. The first energy shell has a single orbital, the 1s orbital. And the reason why the first energy shell can only hold 2 electrons is because an orbital itself can only ever hold 2 electrons. So that explains why the first energy shell can only ever hold 2 electrons, because it's only got a single orbital in it. And that orbital can only hold 2 electrons. So 2 electrons to the first energy shell. So why does the second energy shell then hold 8 electrons? Well, remember there is a 2s orbital. Oops, let's do it the other way. And so this is why the second energy shell is limited to 8 electrons, because the 2s orbital holds 2 electrons, the 3 2p's hold 2 electrons each, so 3 times 2 is 6, and 6 plus 2 is 8. So the second energy shell holds 8. If we went on to the third energy shell, again, we'd have to take into account the fact that there are a total of 9 orbitals, a 3s, the 3 3p's, then the 5 3Ds, that's a total of 9 orbitals, and that would give us a maximum of 18 electrons if we wanted to go there. We're not going to, but I did. But we're not really going to worry about that. But an understanding of the nature of orbitals and energy shells does help us understand why we see this arrangement of electrons. It also helps us understand why chemical bonding is the way it is, and why different types of chemical bonds form, and why the octet rule is such a magical idea, why the presence of 8 electrons in the valence shell is so important, because if those electrons, the first 8 electrons in any energy shell, are always going to occupy the s orbital and the p orbitals. Once we get to the second energy shell and beyond, those first 8 electrons that go into the energy shell are always going to occupy the s orbital and the p orbitals. And it turns out that the s orbitals and the p orbitals in the valence shell are what are responsible for chemical bonding. So once the s orbitals and the p orbitals are full, in other words, 8 electrons are in the valence shell, then the atom is simply unable to form any more chemical bonds. It becomes chemically inert. This is the reason why neon and the other inert gases do not interact with other elements, because their s and p orbitals in their valence shell, which for neon is the second energy shell, are fully occupied. It can't form chemical bonds with other elements because its S&P orbitals are fully occupied. And so understanding the nature of the orbitals, the presence of the orbitals, where they are in the energy shells, what that tells us about the arrangement of electrons in the energy shells, starts to help us understand the behavior of the atoms. So I think you're probably ready for another break because we've just covered some pretty intense ideas. And you might very well want to stop at this point and take a break from everything and just try to think through everything that we've talked about. Maybe go back and take another look at it, replay this last section. Certainly, if you feel like you need a bathroom break or you want a drink or you want something to eat, by all means, stop the recording or turn it off if you really need to walk away. I have a cartoon that I used to put at the end of some of my presentations that I used to give in an honors class that I used to teach. Because we used to get into some really intense topics there, and there was a little boy who was putting his hand up in the classroom and he was going, "Mr. Smith, can I go home? My brain is full." Maybe that's where you're at right now after this one. Take the break if you need it. I'm going to present my next concept question here and then stop for a few seconds, 30, 45 seconds, a chance to think about this, and then we will come back and go through the answer to this question. So the question is, fluorine is element number 9 and sits at the top of column 7 in the periodic table. And we could go back to the periodic table and you can see that, and maybe we will. How many electrons does a neutral fluorine atom have? Name the orbitals and electron shells occupied by these electrons. How many electrons are needed to fill the valence shell? Give that a little bit of thought. I'll come back in about 30 to 45 seconds and show you and walk you through the answer for this one. Okay, let's take a look at this question. Now, if you have your textbook handy, you can take a look at the periodic table that I've got here in the presentation, because this is just a copy of the periodic table that comes from the textbook. So here's fluorine, element number 9. It's sitting at the top of column number 7. This is column number 7 in the periodic table. So being element number 9, that means it has 9 electrons. The first 2 electrons are always going to occupy the first energy shell. So the first energy shell has electrons in it. The remaining electrons, that being 7, are not enough to fill the second energy shell. So all of them will fit quite comfortably into the second energy shell. So the first energy shell and the second energy shell are the shells that are occupied. 2 electrons in the first energy shell, 7 electrons in the second energy shell. Now it also asked, the question also asked about the orbitals. We know the first energy shell has just one orbital, the 1s, so that one must be occupied. We know that there are 4 orbitals in the second energy shell, the 2s and then the 3 by 2p's. So 2 of the electrons are going to go into the 2s and it will be fully occupied. That leaves us with 5. And that means we've got enough to fully occupy 2 of the 3 2p's plus 1 to go into the third 2p. So all of the 2p orbitals plus the 2s orbital in the second energy shell will also be occupied. How many electrons are needed to fill the valence shell? We'll remember again, 8 is the magic number. And for the second energy shell, not only is it the magic number, but it is the total number of electrons that can fill that will fill the valence shell. So it's got 7, it's got room for 1 more. So that's the answer to our concept check question. And in reality, you didn't really need to have that diagram, the periodic table. All the information that you needed was right here. And really all you did need was that it is element number 9, sitting at the top of column number 7. That's not really essential. That's a distractor. The only information you really needed was that it was element number 9. From there, you could figure out everything else. So now we need to really talk about chemical bonding. And chemical bonding is, again, a function of what the element needs to do to look like an inert gas. Does it need to give up electrons, or does it need to gain electrons in order to look like an inert gas? And the reality is that while we can make some statements about whether it's going to give up electrons or gain electrons on the basis of its position in the periodic table, so if it's in the first 3 columns of the periodic table moving left to right, it's going to want to give up electrons from column 4 through column 7. It's going to want to gain electrons. Remember, column 8 is the inert gases. So they're not going to gain or lose anything. But the reality is that giving up electrons or gaining electrons is a function of another idea that really is the governor of whether they're giving up electrons or gaining electrons. And that is the concept of electronegativity. And you can see the term down here. Electronegativity. This is a term that we're going to be using over and over again. We're going to come back to this many, many times. Electronegativity is a function, or is the term that we use to describe how strongly atoms hold on to their own electrons and how easy it is for them to capture electrons from other elements or from other atoms. So it has 2 components. How strongly do they hold on to their own electrons, and how strongly can they pull on electrons from other atoms to drag them away from other atoms? In other words, capture electrons from other atoms. And we can also create periodic tables that indicate electronegativity. So here is a very highly modified version of the periodic table that takes into account electronegativity. And so over here we have the atoms that are considered to be strongly electronegative. And over here we have atoms that are considered to be weakly electronegative. So let's see, just erase this blob. So these are strongly electronegative, and these are weakly electronegative. And what you also start to realize is this represents the right-hand side of the periodic table, and these represent the left-hand side of the periodic table. So columns 1 through 3, and these are columns 4 through 7, basically. So we start to take this into account. The most strongly electronegative atom of the lot is fluorine, and fluorine is actually able to take electrons away from pretty much every other element that it comes in contact with. Fluorine is very, very strongly reactive. Chlorine, we've already talked about previously as being strongly reactive. You can see that it's over here on the strongly reactive side of the periodic table, strongly electronegative. This is why chlorine bleach is so reactive and strips stains out of materials. It's really altering the electron makeup of the stain material. It's stripping electrons out of that staining material and changing it chemically that way, because it is so strongly electronegative. But we should also take note of the position of the elements that are most important to life. So oxygen, which it turns out is the second most electronegative element of all. Nitrogen, also somewhat electronegative, but not as electronegative as oxygen. Carbon sitting here, and hydrogen, which in terms of electronegativity, carbon and hydrogen are pretty much equal. So carbon and hydrogen are considered to be equal in terms of electronegativity. This is showing hydrogen as being just a little bit more electronegative than carbon, but they are so close to each other that they're considered to be more or less equal. And it's the difference in electronegativity between the elements that are interacting with each other that determines, are they going to give up electrons? Are they going to gain electrons? Are they going to have to share electrons? Because those are the three options. You can give up an electron or more. You can gain an electron or more. Or if you can't gain or give up electrons, your only alternative is to share. And that basically establishes the nature of the chemical interactions between elements. Are they giving up electrons? Are they gaining electrons? Are they being forced to share electrons to accomplish the task? So let's take a look at the different types of chemical bonds. So the first type of chemical bond, and the chemical bond that links atoms together to form molecules, are called covalent bonds. And the name of the bond tells you what's going on here. So co means to share, and valent is electrons in the valence shell. So a covalent bond is shared electrons in the valence shells of the atoms that are involved. So we recognize that there are two types of covalent bonds. One is called nonpolar, and it's actually addressed here on the slide, but I want to put the note that on one slide for you. And then polar where the electrons are shared unequally. So what determines the nature of, or what determines whether it's going to be polar or non-polar? The difference in electronegativity. So it really does come down to electronegativity. The electronegativity is what is determining that the sharing needs to take place. So if you're not electronegative enough to take electrons away from another atom, in other words, you're close in electronegativity, or you're equal in electronegativity, then your only option is to actually share electrons. But no one said that those electrons had to be shared equally. And the way I illustrate this is possibly something that you're familiar with if you have brothers and sisters. How you go about sharing with your brothers and sisters is usually determined by, are you older or younger? So suppose your mother comes out with a candy bar and says, share this. If you're younger than your brothers and sisters, you know that you're likely to get a share, but it's not going to be an equal share unless you have an unusual family. You're going to probably get a smaller share, because while mum said share, there's no reason why the sharing has to be equal. But if you are sharing between equals, then you're likely to get equal share. And so that's basically what's going on here in the formation of covalent bonds between atoms. If they are equal in electronegativity, then they share the electrons equally. If they are unequal in electronegativity, they'll still share the electrons, but they don't have to share them equally. And so we get these two types of covalent bonds, polar and non-polar. So in the case of hydrogen, where the two atoms are both hydrogen and are therefore equal in electronegativity, the electrons are going to be shared equally. So the electrons get shared equally and they form a non-polar covalent bond. And we can actually diagram this in this fashion. So that bar linking the two hydrogen symbols together represents the shared pair of electrons. So if we've got two oxygens, oxygen has 6 electrons in its valence shell. It would like to have 8. As a consequence of that, sharing a single pair of electrons between two oxygen atoms is not going to be enough. They need to share 2 pairs of electrons. Because they are both oxygen atoms and therefore equal in electronegativity, even though oxygen is the second most electronegative, both are oxygens, so they are equal in electronegativity. They're going to share a pair of electrons, and we would represent it this way. It's not an equal sign. It's 2 bars representing 2 shared pairs of electrons. If we've got nitrogen, again, nitrogen's relatively electronegative, but it has 5 electrons in its valence shell. It's element number 7. And sharing 1 pair of electrons is not going to do it. Sharing 2 pairs of electrons is not going to do it. But sharing 3 pairs of electrons would get the appropriate number of electrons in each space. Because notice what's happening here with the hydrogen. If I draw in the electrons, those electrons are going to occupy this combined space now, and this combined space surrounds the 2 nuclei. So as far as each nucleus is concerned, there are 2 electrons in this combined space. So both of them perceive, and here I'm anthropomorphizing a bit, both of them perceive the presence of 2 electrons in their valence shell space. Likewise here, these 2 oxygens perceive the shared pairs of electrons as being in their combined space. And so as far as the 2 nuclei are concerned, there are 8 electrons in the valence shells. Likewise with the nitrogens here. The 3 shared pairs of electrons are occupying a combined space, so as far as the 2 nitrogen atoms are concerned, their valence shells are fully occupied because they have the appropriate number of electrons circulating in this combined space. So there are a maximum of 3 covalent bonds that can be formed between 2 identical atoms. And you might ask, well, why can't you do it with carbon? Because carbon can form 4 covalent bonds. Well, physically it can form the 3, but the 4th or the potential 4th covalent bond is simply geometrically in the wrong location. And you can't bend this around to form the 4th covalent bond. So 3 is the maximum number of covalent bonds that you can form between any 2 atoms. Even though carbon could potentially form a 4th, it can't actually form it because physically it's in the wrong, the bonds are in the wrong location to form up. So that's the non-polar covalent bond. And this diagram simply illustrates in terms of electron diagrams, the sharing of electrons. So you can take a look at this one as well. And again, it's taken directly out of the textbook. So it would be helpful for you to look at this. So where do the polar covalent bonds come from? Well, this is where the sharing of electrons are unequal. This would be you with your older or younger sibling, depending on which end of the relationship you're at. In the case of oxygen and hydrogen, sorry. Oxygen is extremely electronegative. And hydrogen is moderately. Neither is electronegative enough or weakly electronegative in the case of oxygen is not electronegative enough to pull an electron away from hydrogen because hydrogen is electronegative enough to hold onto its electron. So they really do have to share. But because oxygen is more strongly electronegative, it gets the biggest share of the electrons. And what do I mean by a bigger share? Well, what that really means is that the electrons spend more time at the oxygen end of the bond, that combined space that represents the bond, than they do at the hydrogen end of the bond. So if we draw this up, well, actually, there's a diagram on the next page. So let's go to the diagram on the next page to see this. So the electrons that are in this covalent bond are going to be more up here at the oxygen end of the bond and less down here at the hydrogen end. And likewise over here, we're going to be more at the oxygen end of the bond and less at the hydrogen end of the bond. And so this end of the bond is going to have a negative charge, which we describe as a partial negative. And we use this squiggle, which is actually the lower Greek letter delta, to indicate the partial charge. So this is a partial negative. And there are, in fact, 2 of these, because there's one associated with this covalent bond and there's one associated with this. So there should actually be 2. And then at the hydrogen end of the bond, because you've moved the negative charge towards the oxygen, what you're left with is a positive charge, but it's again a partial positive. And as you'll see next week, the presence of these polar covalent bonds and these partial charges, that tells you everything about that you need to know in terms of what causes the properties of water. They all trace their origins back to the presence of these polar covalent bonds and the presence of these partial charges, but that's for chapter 3 next week. But the reason why you have these polar covalent bonds is because oxygen is far more electronegative than hydrogen. And so the electrons tend to spend more of their time at the oxygen end of the covalent bond rather than the hydrogen end of the covalent bond. Oxygen sees the electrons more of the time, which leads to that uneven distribution of the negative charge. The second type of bond occurs between atoms that are significantly different in electronegativity. And so it's typically between one that is very weakly electronegative and wants to give up an electron. That would be columns 1 through 3. They all want to give up electrons. And elements that want to gain electrons and are physically capable of gaining electrons very easily. And the ones that are most frequently referred to there are the elements in column number 7, otherwise known as the halides. Chlorine is a really good example of that. And so chlorine is, and sodium are typically the elements that are used to exemplify this. And if you recall, sodium and chlorine are the elements that make up sodium chloride, table salt. So table salt is a product of ionic bonding. And what happens is that sodium, being very weakly electronegative and having this one electron that it wants to get rid of so that it looks like a noble gas with this shell being its valence shell. It wants to give up this electron. Chlorine, remember, is very strongly electronegative. It's usually considered to be number 3 or number 4 on the electronegativity scale. It has the ability to not only want an electron, but able to capture an electron. So the electron is transferred across. That means that now sodium has lost a negative. That's pretty disgusting there, isn't it? It's lost a negative. And the chlorine has gained a negative. So having lost a negative, the sodium now has more positive charges than negative charges. It has one extra positive charge. And so it is considered to be a sodium ion. An ion is an atom or a molecule that has gained or lost an electron. As a consequence of that gain or loss of electrons, it's now taken on a charge. So sodium loses an electron, it now becomes positively charged. Positively charged ions are known as cations. And sodium is said to be a sodium ion with a +1 charge. The chlorine, having gained a negative charge, gained an electron, now has one more negative charge than it has positive charges, protons in the nucleus. And so it is now a chloride ion with a 1- charge, and any negatively charged ions are referred to as anions. Now, because of this gain in charge, there's now an electrical attraction. So now that you've got these oppositely charged ions, they're attracted to each other. We know positives and negatives attract each other. So these are now attracted to each other, and that becomes the ionic bond. A salt crystal is simply a lot of sodium ions and chloride ions attracted to each other by these opposite charges, and they form a regular array of sodium ions and chloride ions. Each sodium is surrounded by 6 chloride ions. Each chloride ion is surrounded by 6 sodium ions. But the ratio of sodium ions to chloride ions within the crystal is always 1:1. So that's why we say that sodium chloride, I'm doing well with this today for some reason. So yes, we do say that the chemical formula for sodium chloride is NaCl, but bear in mind that there's no such thing as a sodium chloride molecule, because by definition, molecules are formed by atoms linked together by covalent bonds. These are not covalent bonds, these are ionic bonds. The other thing to bear in mind is that salts, of which sodium chloride is an example, are very stable in the absence of water. But when you put a salt into water, it dissolves very easily. This is a principle that is recognized by the pharmaceutical industry. Drugs, the vast majority of drugs are produced as salts. And the reason why is because, as the notes just said, salts are extremely stable so long as everything is kept dry. And pill bottles come with the drugs in a dry environment, and they usually put little dryer packets in there to keep everything dry. And then when you swallow it, of course, it's going into a very damp environment, a wet environment, which means that the salt will dissolve, and one of the two ions that are released when it dissolves is the active drug. This is a trick that the pharmaceutical industry has been using for many years now. It allows them to produce drugs that will remain stable as long as everything's kept dry, but becomes usable as soon as you put it into the body where there's a lot of water. It's just a little chemical trick that the pharmaceutical industry uses. So that's two of the three important chemical bonds for biologists. The third is called hydrogen bonding. And hydrogen bonding is going to become really important to understand the behavior of proteins and DNA, nucleic acids, and also in terms of the property of water. And it comes about because, remember that the bonds, the covalent bonds in a water molecule are polar, so we have these partial charges on them. Well, nitrogen and hydrogen do exactly the same thing. Nitrogen is electronegative enough to form polar covalent bonds with hydrogen, and these partial charges on the hydrogens and on the oxygen ends of the covalent bonds are attracted to each other. So the partial negative here is attracted to the partial positive, and that electrical attraction is the hydrogen bond. I'm not sure what's got into my hand this morning, because I seem to be struggling to write. It's not what I wanted. There we go. Got it back. So it's this electrical attraction between the opposite partial charges that represents the hydrogen bond. And we'll talk a lot more about these when we talk about water next week, and we start talking about the large biologically important molecules when we get to chapter 5 in a couple of weeks. So you're going to learn a lot more about these hydrogen bonds in the upcoming chapters. Then there are some very weak transitory interactions called van der Waals forces. We don't talk about them very much in this class, but they do exist. And this is because on the surface of many large molecules, you have these fleeting positive and negative regions in the molecule as the molecules keep moving around. And those weak attractions can still be significant under some circumstances. They can still attract each other. So we just need to be aware that these exist. We're not going to talk about them very much in the class because in terms of the molecules that we're actually talking about, they're not particularly significant. But you do need to be aware of the fact that they do exist. You'll possibly talk about them in a lot more in some later, more advanced classes where they'll become very significant in the discussion of some of the molecules that you might be talking about. But as far as we're concerned, no, they're not of significance. So the final piece of the puzzle before we take another break, and I realize that we're covering a lot of material in this presentation, is getting up there in terms of time, but that's why the breaks are there, is to recognize that these interactions between the atoms as they form their chemical bonds is going to give rise to shapes of the molecules. The molecules are actually going to take on particular shapes because of these interactions between the atoms. And we need to talk a little bit about where those shapes come from and why that might be important. So we have a number of different ways of diagramming the shapes of molecules. We can use what's called space filling. We can use ball and stick, and I'm going to show you some models in a moment that are ball and stick models. And then you can also show these types of diagrams that show you where the bonds are and how they can be formed from the various electron arrangements of the atoms. So one of the things that I want to show you by way of models, just so that we start to understand why this is so significant. Here is a ball and stick model of a methane molecule. And you can see that it's extremely symmetrical. If I hold this face towards the camera, you can see that this face is an equilateral triangle. And in fact, it doesn't matter which face I show you, each side is an equilateral triangle, and it forms a shape called a tetrahedron. And you can see the tetrahedron shape here on the slide in 2 dimensions. And the issue is that the carbon at the center, and you can see the carbon here at the center, from which these lobes are radiating out. So the carbon is in the center here. Let me draw that in just so that it's clear. This is the carbon sitting in the center. And this is where the hydrogens are going to be in methane. Okay, they're on those lobes. And we really do know that this is the shape of methane. It is well understood that this is the shape of methane. The problem for us is to understand how we get from this shape, from the S and the P orbitals, and these are the S and the P orbitals, in the valence shell of a carbon atom, which happens to be the second energy shell. So there is a 2s orbital, and there are 3 p orbitals orientated on the x, y, and z axis of 3-dimensional space. These are the orbitals that are involved in forming the covalent bonds that are linking the hydrogens and the carbons together to form methane. So how do we transition from this to this? And this is the transition that we're talking about. How do we go from these S and P orbitals to these what are known as hybrid molecular orbitals? And the answer is, it's all about the hybrid. And a hybrid is simply a new item formed by merging together 2 existing items. So let me see if I can put that in as a note here. See if I can get those. I've taken it back and I can't. Okay, anyway, it was easy enough to put the pencil. Just got to be careful about pushing random buttons on the pen. It's got 2 buttons, and if I push the wrong one, I eliminate what I've just written up. So hybrid. Forming something new. So just as a quick example, a hybrid car. Many hybrid cars have a gasoline engine and an electric motor. Those are 2 separate ways of driving a car. In fact, early cars were electric, but because gasoline turned out to be a more efficient way of doing it, they became predominant. But now with new battery technology, battery-powered cars are more common. But hybrids were the first attempt to move away from gasoline as a way of powering a car. And so they took two existing technologies, gasoline engines and electric motors, and created a new type of car, a hybrid car, one that combined two existing technologies, gasoline technology and electric motor technology, to create the hybrid technology. So it's taking two existing things, merging them together to create something new. And that's what happens here. The hybrid orbitals So that's the origin of these hybrid spaces. They are the merging together of the s and the p orbitals, in this case, as far as carbon is concerned, the 2s and the 3,2p orbitals, to create four new spaces, which are the hybrid orbitals. And so I can show you another carbon atom, which has already got one hydrogen on it, but here are the other three hybrid spaces. And you can imagine that there would be a fourth one here, which I don't have illustrated right now. But here are the hybrid spaces formed by combining together the S and the P spaces and then rearranging them into these four hybrid spaces. And because carbon has 4 electrons in its valence shell, it can insert an electron into each of these 4 hybrid spaces, but they're orbitals. They may be hybrid spaces, but they're still orbitals. And remember, an orbital can hold 2 electrons. These orbitals only hold 1 electron, which means that there are 4 electrons still, and the valence shell is not filled. But by filling these molecular orbitals, we can fill the valence shell at the same time. So when a hydrogen comes along and merges its 1s orbital with one of these hybrid spaces, you get a shared pair of electrons, a combined space formed by the molecular orbital and the s orbital of the hydrogen. And the 2 electrons now share this combined space. And you have a covalent bond, and it is nonpolar because carbon and hydrogen are nearly equal in electronegativity. So this is a nonpolar covalent bond, shared pair of electrons. If a hydrogen does it with this molecular orbital and this molecular orbital and this molecular orbital, we wind up with this, methane. And because now each hydrogen sees 2 electrons, and the carbon sees the combined 4 shared pair of electrons with the hydrogens, each of these atoms now has a valence shell configuration that looks like a noble gas. And there's no further reason to share electrons with anybody. And so methane is 1 carbon and 4 hydrogens with this symmetrical shape, because each of these molecular orbitals are equal. And so it has a symmetrical shape. All atoms that are forming covalent bonds are doing this hybridization between s and p orbitals in the valence energy shell. So remember, the valence energy shell could be the 2nd energy shell, 3rd energy shell, 4th energy shell. Doesn't matter which energy shell, it's the s and the p orbitals in those energy shells that are going to be hybridized to give the 4 molecular orbitals. But if it is not carbon, it may have a different number of electrons to place into those 4 orbitals. So if we think in terms of oxygen forming water, and you can see oxygen forming water down here, oxygen is element number 8. it has 6 electrons in its valence shell as a consequence. So once it's put 1 electron into each orbital, it's still got to fit 2 more in. And if it does that, then 2 of these orbitals are going to have 2 electrons in them. And so they're no longer available to form covalent bonds with other atoms. So you've only got 2 molecular orbitals now that can form covalent bonds with hydrogen. And so hydrogen bonds up here, hydrogen bonds here, and water becomes H2O. These 2 orbitals are still present with their electrons in them, and they do influence the shape of the water molecule by putting strain on the molecule and actually forcing these to get a little bit closer together than they might like. And so we know that the angle here in the water molecule is a little bit different from what we might expect. But again, it's all explainable by looking at these hybrid orbitals and what happens once the hybrid orbitals form and we put electrons into them. Do we need to go into any more detail rather than this? No, because what we're really trying to get at is molecules have very specific shapes. And those shapes determine the interaction between molecules. So here we have morphine. Morphine binds to receptors on the surface of cells in the brain. The problem is we don't understand why morphine binds to these receptors, because we don't go around chewing on opium poppies from which the opium that is converted into morphine is derived. There's no logical reason why we should have receptors for binding morphine. And for a long time, pharmacists and biochemists and biologists in general were puzzled as to why morphine worked. Why did it bind to pain receptors and become a pain blocker? And then about 25, 30 years ago, maybe a little bit longer than that, probably closer to 40 years actually, as I think about it, a new class of naturally occurring chemicals were discovered in humans first, but in other animals as well. And they've become known as endorphins. And the term endorphin is a contraction of 2 words, endogenous or naturally occurring morphines, because the endorphins are actually the molecules that bind to these receptors. They are the target of these receptors. But when we start looking at the endorphins, these endogenous morphines, these naturally occurring morphine-like molecules, we now start to understand why morphine works, because this area of the endorphin and this area of the morphine molecule are exactly the same. And these are the portions of the molecule that bind to the receptors. Morphine works because it mimics the structure of the naturally occurring molecules. That's why morphine works as a pain blocker. These are our natural pain blockers, our natural feel-good molecules. They're involved in making us feel good. Just the same way that morphine makes us feel good and makes us feel no pain. The drawback with morphine is that it also affects the control regions of your brain that controls breathing and controls heartbeat, and it suppresses those. So if you take too much morphine, it'll actually slow down your breathing and slow down your heartbeat to the point where you die. And that's what happens when you overdose on morphine. Why do you overdose on morphine? Because morphine requires more, you require more and more morphine as you go to get the same feeling, because your body acclimates to the effect of the morphine. And so if you want to get a high, you have to take more, and eventually you get to the point where the morphine is not only giving you a high, but it's also starting to block or suppress your breathing and your heart rate. And when you take enough of it, it kills you. The natural endorphins will do the same thing, in that you need to generate more of them to get the same pain blocking effect. But fortunately, they don't have the effect of suppressing your breathing. So if you find people who are committed to exercising, addicted to exercising, addicted to eating chocolate, because yeah, chocolate will do the same thing. It's because they're addicted to the endorphins. The big advantage of the endorphins is, well, they'll make you feel good. They don't suppress your breathing and they don't suppress your heart rate. So a natural high is always better than a chemically induced high. So that's the reason why understanding the shapes of molecules is so important. And that's the reason why we've done this area on talking about the shapes of molecules, while we've talked about bonding, talked about how atoms interact with each other, so we can understand why molecules have particular shapes, because it's all about the shape of the molecule that determines its interactions with other molecules. So one more break before we talk about the last little bit. And here's the concept check. Why would a pharmaceutical researcher want to know about the three-dimensional shape of naturally occurring sigmomolecules? That shouldn't be a difficult one to answer now. But let's stop for about 30 seconds. Of course, if you want to go take a bathroom break, feel free to do so. Pause, turn it off. Remember, it doesn't bother me, because I'll still be here when you come back and I won't know that you've done it anyway. Okay, so let's talk about this so I can finish out the chapter and the presentation. Why would it be important? Well, it comes back to this. If you are trying to create a drug, remember morphine is a drug, it's a derivative of opium. It's a chemical modification of opium, but it's still a drug. If we wanted to create another drug to target these receptors, say we were the pharmaceutical researchers that were creating OxyContin or oxycodone. Those are synthetic opioids. So an opiate is a naturally occurring chemical or derivative of a naturally occurring chemical. So opium, morphine, and heroin are referred to as opiates because they are derivatives of the naturally occurring chemical opium. OxyContin and oxycodone are referred to as opioids because they are synthetic versions. So why do they work? Because pharmaceutical chemists figured out what is the relevant part of the molecule to bind to the receptors. So they were looking at this structure and they created a synthetic molecule that contained this structure so that it would bind to the endorphin receptors. That's why the opioids work, because they mimic the opiates. So why would a pharmaceutical researcher want to know something about the three-dimensional structure of a signaling molecule? So that they can design a synthetic molecule, a drug, or a molecule that they would like to use as a drug, that mimics the shape of the naturally occurring molecule so it will bind to the same receptors. And we know enough now about receptor molecules. We have enough computing power that we can create very accurate models of receptors. We can create very accurate models of the naturally occurring chemicals that bind to those receptors so that we can design of molecules that will mimic the behavior of the naturally occurring molecules, and in some cases bind even better. That's the big issue with oxycodone and oxycontin. They bind to these receptors even better than morphine. They are much more powerful painkillers, but they're also much more powerful addictive drugs, and smaller amounts of them can cause more problems in terms of overdoses. The worst one of the lot, fentanyl, which is the latest designer opioid, and has been banned completely. The manufacturer has been banned completely here in the United States, and it is illegal to both manufacture it and import it. And so fentanyl is now imported illegally, and in some cases used to mix with morphine and heroin for street addicts. And unfortunately, they don't realize that it's there. And fentanyl is such a powerful opioid that it's so very easy to overdose on it. And so this is the reason why there's been this crackdown on fentanyl. It is so powerful. But again, it's a designer chemical to mimic the morphine, the structure, the portion of the morphine molecule that binds to the endorphin receptors. So that's why pharmaceutical researchers need to know something about three-dimensional structures of the molecules that they're trying to mimic. It allows them to create the molecule that the mimic molecule to reflect the shape of the original. So let's talk a little bit about the last part, and that's to talk about chemical reactions. In chemical reactions, we have the conversion of reactants, the chemicals that are at the starting point and typically are on the left-hand side of the equation, that are converted into products. And so we could write a generic chemical reaction by saying, oops, let's go back, turn on the pen again. A plus B gives C plus D, and these would be the reactants. And these would be the products. And you'll notice that I've drawn in here what we often refer to as the bidirectional arrow. Sometimes we draw it that way, sometimes we draw it this way, sometimes we'll draw it this way. These are all equivalent bidirectional arrows. What does that mean? It means that any chemical reaction that is left to its own devices, in other words, runs in isolation, will reach a condition called equilibrium. And at equilibrium, it's important to recognize that there is no implication of equal amounts. That's not what equilibrium means. Equilibrium means that the rate of chemical reaction or the rate of movement in one direction is equal to the rate of movement in the opposite direction. So it's very important to recognize that. We will talk about equilibrium a lot throughout the semester with respect to chemical reactions and with respect to some other processes that are important to cells. But we need to remember under all circumstances that equilibrium is best understood as equal movement in each direction. So the rate of movement in one direction equals the rate of movement in the opposite direction. At the same time, we also need to recognize that there is going to be chemical alterations, because another feature of chemical reactions is that you're going to be breaking existing covalent bonds and forming new covalent bonds. This is also part of a chemical reaction. So this is something that you must also be aware of, that the nature of a chemical reaction is the breaking of the existing covalent bonds. It's not just breaking any bonds, it's breaking covalent bonds and forming new covalent bonds. In the process, the atoms that are present are going to be rearranged into different types of molecules. But throughout all of this, no atoms are destroyed, no atoms are new atoms are produced, and this is known as the law of conservation of matter. What goes in must come out. You can't make matter disappear. You can't make matter magically appear in a chemical reaction. So if we take a look at a specific chemical reaction, here's the reaction involving the combination of hydrogen and oxygen to produce water. So here you can see the existing covalent bonds between the hydrogen atoms and the oxygen atoms. And when we carry out the chemical reaction, we get new covalent bonds forming between hydrogen and oxygen to form water molecules. But the number of hydrogens on this side and the number of oxygens on this side equals the number of hydrogens and oxygens on this side. No new atoms formed, no atoms disappeared. So this is the notion of conservation of matter. What goes in comes out. It doesn't necessarily have to come out in the same form. So that's the key understanding here. That what goes in comes out, but you form new different molecules in the process. So what is the big deal in terms of equilibrium? Well, remember, equilibrium is reached by a chemical reaction if it's carried out in isolation. So if you were to do a chemical reaction in a test tube, it would eventually reach equilibrium. And the rate of movement in the forward direction would equal the rate of movement in the opposite direction. And that's bad news for cells. Because if we are using chemical reactions to manipulate energy, if the rate in the forward direction equals the rate in the movement direction, in the opposite direction, then any energy manipulation in the forward direction is going to be matched by reverse manipulation in the opposite direction. In other words, there's going to be zero change as far as energy is concerned. And so for cells, chemical equilibrium is not a good thing. And we're going to spend a lot of time thinking about the nature of chemical equilibrium and how cells can avoid reaching chemical equilibrium. Because if you want a really good definition of chemical equilibrium, death. Death is chemical equilibrium. And so for cells, chemical equilibrium is a really good thing to avoid. But remember again, equilibrium is a function of all chemical reactions if they are operating in isolation. The rate of movement in the forward direction will always at some point equal the rate of movement in the opposite direction. Nothing is implied about equal amounts. That should not be misconstrued. There is no implication of equal amounts when we use the term equilibrium. But what is meant is that the rate of movement in the forward direction is equal to the rate of movement in the opposite direction. So let me just highlight that here. This is the really, really important definition of equilibrium. I can't emphasize this enough. You have to make sure that you understand that this is the appropriate definition of equilibrium. So that brings us to the end of this presentation, but there's always time for one more concept check. So here is the final concept check. Define equilibrium. What type of reaction, if any, occurs faster at equilibrium? The formation of products from reactants or the formation of reactants from products? Let me stop for about 30 seconds, give you a chance to think about that one, and then I'll give you the answer. Okay, so this one shouldn't take very long to think about because we've just been talking about it. What is equilibrium? Equilibrium is defined as the rate of movement in the forward direction equals the rate of movement in the opposite direction. Learn that definition and you can't go wrong. What type of reaction, if any, occurs faster at equilibrium? The formation of products from reactants or the formation of reactants from products? Well, if our definition is the rate of forward movement equals the rate of reverse movement, neither of those reactions occurs quicker. Both of them occur, but they occur at the same rate. The rate of forward movement equals the rate of reverse movement. So the rate of formation of products from reactants will equal the rate of formation of reactants from products at equilibrium. That is the definition of equilibrium. So we are done with this presentation. Next comes the properties of water. That's chapter 3. That will be the subject of the next presentation. So I will see you at that presentation, probably next week. Bye for now.